Okay, sorry I'm a bit late on this stream. The stream was originally supposed to start at 8:30. However, I got home a bit late from work, so unfortunately it didn't actually turn out to be 8:30 at all. So now it's 9 o'clock, half hour later after the stream was supposed to start. But it doesn't look like there's anybody watching right now. It was watching then or is now, so it should be fine. This video will be archived anyways for anyone who wants to watch it afterwards, so let me just get into it right now. So here I'm going to go through the basics of how to do C programming with Hacker's Edge. The first thing you'll need is you'll need to get the CC65 toolkit along with the Hacker's Edge dev kit here. As you can see, all you have to do is just download this. I've already downloaded it and I've already extracted it. I'll show you the contents of it. The contents of this zip file is just this directory here. Essentially, it's all it is. Just the zip file makes it easier to download it, to actually be able to use it. And I'm also going to go to, if you go to CC65, or actually there is, one second, there's a better site actually, I just remembered that, CC65. There's like a GitHub, there it is. This is the version you want here, this is the new site actually. This is their new website here. So as you can see here, it says the 6502C compiler, and here you just want to go to, I think, the getting started, or if you click for the Windows version, you just click here. You should get a zip file for the Windows version. Bring it to SourceForge. And the Linux version, compiling it is super easy. Just go to GitHub, do a checkout. It works equally simple on Mac. Just check it out, run make, and it'll just compile it, and you're good. For Windows, just download the snapshot. That's all you really need. And then you also need the dev kit as well, like I mentioned a bit earlier. Just download the zip file. The zip file contains everything in here. You can see the individual files yourself here, but just download the zip file is just more convenient. Okay, and with that out of the way, for how to get the C compiler and the libraries, I'm going to show you what's in the library directory. So here is, 1 second here. Okay, so here's the contents of the zip file that I just extracted, as you can see here. So this is the basic README file. I'll go through this right away. That's what's displaying back there. I shown a similar file when we looked at the assembly one. We looked at the assembly introduction 2 days ago. This file is for assembly coding, not for C coding. This file is also for assembly coding, not for C coding. This make file here makes it easier to basically create your bin files. I'll show you how that works in a bit. And then this file here is not technically required for the C. Because the header is already located in the HELib file down here. And then this is a header file that just contains various helper functions. This file is going to grow as time goes on to include more HackerOS include stuff. So with further ado, I'm going to go and show you how. I want to show you the files here, and then I want to create a basic Hello World program, and then from there I want to show you some of the more advanced features if I have enough time. I want to keep the video within 10 to 20 minutes, 30 minutes max, like I did with the assembly one. So here we go. So this is the configuration file that you'll absolutely require in order to make your binary compatible with HackerOS. Not really Hacker's Edge. You can just compile a program and then make it a ROM if you can make ROMs, but only mission designers have access to actually create ROMs for machines. As a player, you won't have access to do that. So if you do make a flat binary file, you can still import it into the game, but it may or may not run as expected. Just putting that out there. So you'd want to use this file to make sure everything is good. So I want to explain the bits of this file. So here is the 0 page that your C program is going to use for storing temporary variables and things like that for you and your C stack information. CS is your code segment. The code segment here starts at 800, and then we have it as a size of 700. 700. What's that size again? 1 second here. I'm trying to remember these. So yeah, that's the size of about 1.8. It's a little under 1.8 kilobytes is the maximum size. If you increase this, you can increase this for a few pages, and it'll make allow you to create larger C programs. And this is the data segment here. Normally this file gets dumped out into DS bin. This file should always be 0 bytes. If it's more than 0 bytes, then there's probably something weird going on, but it should always be 0 bytes. I'll explain why later. But this is your data. This is your data segment is going to start at 300 in memory, and then its size is going to be exactly one page, 256 bytes. And you can increase this. Just don't increase it too much, or it'll get past your code segment. It'll cause problems. But data segment is for like small variables, like integers, pointers, and things like that. Your data segment should not, for C programs, should not contain large amounts of static data. Static data should all go into CS. You shouldn't have strings, you shouldn't have anything large, so I think 256 bytes for the most part. If you want to increase it to a bit more, 512, you can. But for C programs, the data segment is not really used so much as it would be as it is for assembly. And then this is the heap here. The heap is where all your big variable storage, your arrays are going to be stored and everything else. So the data segment basically will have pointers to memory and heap, and that's how C basically manages its stuff. I will show you in a demonstration program what I mean by that, so you kind of understand the differences between C and assembly and other languages if you programmed in like BASIC and other things before. So the heap start location is the CS start plus the CS size. So we go 800 plus 700. That should be D, I do believe. Let me just do a quick check here, make sure that that is what it is. Oh, actually, it's actually at F00. So the heap, actually, I remember that. I was looking at it earlier. But yeah, the heap starts at F00, and its total size is quite large. I think that's 8 kilobytes. So 8 kilobytes for your heap, which is arrays, dynamic string data, user input, etc., things like that, that's 8 kilobytes. If you really need more, you can increase this quite a bit. But wait until Hacker's Edge version 2 comes out, because the kernel is going to have built-in memory management, so your C programs won't actually have this heap section. The kernel is going to manage the heap and everything in HackerOS version 2. Look out for that in the upcoming. I want to say too soon or too late, but sometime soon, I'll have that ready. So, and the defines basically allow you to use these within code. I'll show you what I mean later on. What I mean by that, what these defines do. It's mostly for assembly stuff. You really shouldn't have to work with the defines when you code C stuff at all. And then now here's our segments. The segments explain where each segment is in memory. So your memory is segmented, essentially, right? So we have our 0 page. 0 page is always in the very first 256 bytes of memory. So that's why we have the ZP here, and here we're only allocate. We don't really use that much. And your C program shouldn't have to use much more. Shouldn't be using ZPs at all, because if you're doing pure C code, you shouldn't have to worry about that. In a future tutorial, I most likely should go through how to how to call custom assembly functions from your C code, because that's very helpful for optimizing certain things. But I'll go through that in a future video. This video is going to keep with the more basic stuff without going into assembly, because assembly was the last video. So this video is going to just go with C. Anyways, then this is the actual file contents here. So first we have a header. This you don't have to worry about. This is just written by our library. So if you look here, we have this HELib file. This HELib file contains a header inside. Well, one of the libraries has a header in there to make it compatible with HackerOS. So that's all I have to worry about with the header. Startup code is the C startup code. Once is code that runs once, like initialization code for C, for the C library and things like that. And then code is the actual C code, where your C program is going to live in memory. Read-only data is constants, your static information such as static strings, etc., etc. And these all live in the code segment, as you can see. These are all part of the code segment. So, and the code segment is currently set to 1.8 kilobytes. So that should be quite a bit of memory for all those things. You can always increase this if you really need to add more memory. And then next we have our data, which is which is like it's static data. Well, not really static, but it's not dynamic data essentially. If you create a static array, for example, in C, it will be put into here. So you don't want to create an array, a static array that's larger than 256 bytes right now, or you're just going to run out of data segment memory. So it's loaded. It's originally in the code segment, but then during runtime, the kernel will actually move it over into the data segment section. I'll show you how this works later, how this works afterwards to explain how that actually does it. I'll show you the memory map. And then here you can see these are read only, and this is read write. The data segment's read write. Everything else is set to read only. And then next we come down to the BSS. BSS is our dynamic memory, which we load from heap and type BSS and define yes. And then these here aren't used in assembly, but these here are used in C. These here are for initialization codes, for constructors, for modules, and deconstructors. The constructors are in startup, and the deconstructors are in read-only data. And these are for initializing heap, initializing other things, perhaps sockets if I enable the proper module support for that, etc. And then these are symbols down here. So we have our stack size. This is the C stack size. This stack size is actually not used for assembly code. So if you're looking at the previous tutorial, this is not used. Well, you could use it, I guess, in your you could reference this variable if you wanted to in your assembly code, but this is used for the C code. So this is your stack. Your stack is 512 bytes in size. The stack is essentially where C pushes arguments to and then pulls arguments back and stores local variables for the current function you're in. So the stack is used for local variables and things like that for your current function call, and also used for pushing data to and from functions that you're calling. So this is why data doesn't really matter too much. So why data can be 256 bytes, and it shouldn't really matter because data, as I say, is very sparsely used when it comes to C programs. It's more of an assembly language thing. And then we have our I/O base, which is the Hacker's Edge standard I/O base section, and then JSR table. This is again for assembly code, where the JSR table resides for the kernel inc can reference it. So if you go into kernel inc, you'll see JSR table everywhere. If you go to here, you'll see the I/O tables being imported. These are both assembly include files. You don't have to worry about these for C programming. And now we'll go into the header file for HackerOS. So these include various functions that you could use. This file is definitely going to be growing in time. Right now, there's quite a bit of functions here that are very useful, but there still needs to be more soon. So we have get param, which this would be a good one to actually demonstrate. This allows you to get the parameter you type at the command line. Load file, so you can basically load in a file. You can read in a file from your OS into a certain address. This determines if the network's up or not. Start a server, close. Reply back. Do a reply if you're a server in server mode in a callback. Send data from the client to the server. Connect to a server. Receive data from the server. And then A to N is ASCII to network, and this is network to ASCII because it's very inefficient to store an IP address as well. How many bytes can an IP address be? It can be like maybe 16, 19. I can't remember. It can be fairly big if you just store it as is. But if you store it in memory as 4 bytes, that's much more efficient storage. That's what this does here. And in order to use these functions, you have to essentially store it as a 32-bit int is what the IP addresses are being stored as here, as you can see. IP address type is an unsigned long. So anyway, so that's those are the header files you have to know about. And 14 minutes already. This video might actually be 30 minutes long then. Okay, and here is the make file that we'll be using, and you can use as well because it's in the zip file. It makes it easier to essentially, get working with it. Some of these are good for troubleshooting. Some of these are just are very helpful. Like this one here, we're going to use quite a lot. And then of course there's another one I believe, or I don't have that one here, but I will demonstrate these in a bit. Okay, so now let's create a file here. So I'm going to get our file up. So we're going to create a basic hello file. So I'm going to refresh this and open up hello C. Okay. Okay. So here, so in this file here, it's going to demonstrate static strings as well as the heap. So the first thing you're going to want to do is you're going to want to do include standardIO.h, and main is going to be it returns an int because you can always return 0 at the end, and then we're going to use the puts function as for our hello world. So two double quotes, hello world from C. And there is a very simple program. Don't worry, I'll get more complex than that in a bit. I'm just doing this as a pure example for now. So next we go make hello.bin. Boom, there we go. So it runs cc65 on hello C. It runs CA65 on the assembly program, and then it runs the linker. So you use the config file, you output the bin, and you link hello O and HELib, and then we remove those other files if you don't really want them around. And just to show exactly how everything looks, we're going to use a hex dump on hello bin here, just to give you an idea what it looks like. So here is the hello world program built in C. So the header is at the top here. This is our header piece up here. And then our code, I believe, starts off right around here, I think it is. So, and then as you can see, we have our hello from C. So now let's try running it. So I'm going to copy this into my debug.fs. For you would upload it to FTP or use the import tool. I might actually show the import version, or actually with this one I can't because there's the header. The header is the problem with using the import. So using the in-game import thing might not really work very well. So yeah, so now if I type hello world from C, it runs. Yeah, because there's the import command, but I don't know if I can actually easily run that, if I can easily use it, because I need to make sure I know the exact header length, and then I need to be able to jump directly after it. Or I could try to prune. Well, actually, I can try to prune the header. Actually, this would be a good example. I want to try this, see what happens. So, okay, let's put that away for a second. I want to try and use the import command because I'm kind of curious, because a lot of players might not use the FTP, or it might not work for them correctly. FTP is still kind of sketchy at times, so it doesn't want to work sometimes. I'm still working on fixing the bugs there. So what we could do is if you put the header to load in the DS, right? Then we can remove hello bin, then go make hello bin. Now if I do a hex dump -c, do hello bin, here we go. A9 is where it starts. So now here is the headerless version of our code. This code I should be able to import into the game pretty easily. And then under curiosity, if you want to, here's how the header looks. This is just the header. Okay. Actually, it's the start address. I believe this is the size of the data segment. This is where the data segment is. And then, yeah, it's the data segment's at. Data segment's right about, I think it's over here, is it? Yeah, I think that's whereabouts it is. Yeah, and then we have data segment, that's 808. No, this is where you're putting it. We're putting it at 0308, and then 0898 is where we're loading it from. this is the size. Oh yeah, the size. Yeah, it's a long. Yeah, it's a 32-bit. Anyways, so so in order to convert this over, I actually need a copy of my other tool. SM S to hex, and then I need to. Oops. Activate. Okay. And then we need this to be at an 800 load address, so I believe I have to go 800, and then hello bin. Now I should have an output hex. Yep, here we go. Okay, now I should be able to import this into the game server, no problem. So I'm first gonna do a halt actually. Okay, and then I'm gonna run it, boot it up. Oh, that's not good, is it? Okay, ASM s make boot sys. There. Okay, now I should be able to boot it up now. Okay, make. There we go. Now, okay. There we go. We're good. Perfect. Okay, that just makes sure the memory is clean. So next, do a Control D. Gonna do an import. Oh, it's up here, isn't it? No, it's up here. Here it is. Okay. Quite happy of a day off tomorrow. Okay, and then we run back in. Actually, I can actually demonstrate brun now. So import it into 800. So if we go brun 800. Oh. There. Huh. I swear that was working yesterday. But it could also be... Oh, the header's still there. The header shouldn't be there. Unless it built... No, it wouldn't have built hello again. What's going on here? Hex dump -c hello bin. Oh, it's like it's A9. Oh, maybe it's still expecting... Oh, yeah, because this is actually still assembling at that location. Yeah, that's interesting, actually. Because it won't actually work like this. Because the header is still in the top of the... So what I have to do, I keep it CS, but just do that. Or... yeah, that should be fine. There. Now if I make, now I can make, or rm hello bin, make hello bin. Okay, then we do our hex. There. There, now the file's a bit different. There we go. Okay, that's why brun doesn't work. 49.7.30.2. Import it. There we go. Okay, so let's go brun 800. Really? It still says 8. It shouldn't be assembling there anymore, though. It should be putting the startup code here now. Because now the header's at the bottom, so it shouldn't be doing that anymore. Okay, well I just imported it, so let's go into here and take a peek. Didn't even get to the more advanced stuff yet. I really should be doing that right away. Okay, so let's go to the code segment. Yeah, it's definitely not. Oh, that's why. Yeah, because brun, it's running itself. Because I need to actually, I need to assemble it to a different location. Yeah, I completely forgot about that. Okay, so we're gonna go. I want to put this as, since I'm not using the heap anyways, put that at 1A. This is what I did yesterday too. Or did I go A1? No, I did 1A. 1A yesterday. I did 1A yesterday. Or did I do it like this yesterday? No, I did 1A0. Yeah, I did that yesterday. Okay, that should do it. Okay, now if I compile it, I should be able to get there we go. Now I need to put this as 1A. Enter. Cat. There, now it's at 1A. Now I copy this. Go back to here. Do an import. Actually, I can do press up. Tab. Enter. Good. F5. Now I go brun 1A00. There we go. It works. So brun we introduced very soon. But yeah, brun works now. So now if we go hemon, I should also be able to do this in hemon as well. 1A00R. Hello from C. Perfect. Okay, so that's an example on how you can import your C code as well. But in order to import your C code, you have to make sure you move the header out, and then change the CS to this here, or else it's not gonna be able to work at all. And then I want to open up this here for a second, just to kind of show you in memory where it is, so you can see that it loaded up in 1A here. So here it is, 1A. That's the code we just ran. So you can import code using the import tool as well. If you make C code, you can do the import, as long as you place your, as long as you update these things. So now we're going to put it back to 800 because this is how the kernel requires it. Put it back to 800 and then put the header back on the top. There. Okay. Now I'm going to continue on with the examples, with the C examples. So we're going back to hello C here. And I'm going to show you how to allocate memory and things. So, and then I want to show you how it looks in memory, because you don't have access to the memory tool, at least not yet. Players don't have access to a hex dumping tool. A hex dump tool will be available soon. In this case, so we're going to do lib.h, and then we also need con.io for this example. So stdlib is for allocating memory, which almost every program is going to need standard lib. Okay, and then we're going to put in our pointer, so char star. We're going to put our name here. And then we need to allocate our memory, so go name equals, and we need to make sure we do this. malloc. 40 characters should be fine for a name. Then we can keep that there, it doesn't matter. And then do puts. What is your name? Gets name. Then we're going to do this just as an example. We're going to go. I think we need to do string compare, I believe. I believe we have to do string compare. I don't think in C you can do equals directly. I think you have to do string compare. So string compare, with our name. And then do a puts. Puts is more efficient unless you have to do formatting than printf. That's why I'm using puts here, because printf is a very heavy function, especially for 6502 and Hacker's Edge. It just takes a lot of processing power to do printf. So I recommend doing a puts over a printf. This is basically the same program we did yesterday, but in C, as you can probably tell by now. And then puts nice to meet you. And C put C is where we need con.io because we want to put an enter after our name. Okay, I can also guess I've done a string copy, or I concatenate and just added a slash to it, I guess. But yeah, that's fine. So we do that, and then make sure you free your variables afterwards. Don't free your variables, then, well, you know. So there we go. Now let's try running it. C65. Make hello bin. Oop, what? Undefined function string compare. Ooh. Dun. Let's see here. Okay, so here's our documentation here. Let's take a quick look here. So we're going to go to the library. Or no, actually, that's not the one with function reference. Control F, str, CMP. I think this is part of the string function. Yeah, it's part of string age. So we'll need to do string age as well. So okay, put that there. Okay, so okay. How big is our hello bin right now without that extra stuff in it? Only 197 bytes. But now let's do a make. Now watch how large the file has grown. Wow, 1.7 kilobytes just for that. Yeah, C is quite a heavy language, as you can probably tell. So doing C in Hacker's Edge will result in larger binaries, just to let you know. Okay, now let's try running it. So copy this to debug fs. Let's go over. Cross our fingers. Let's go Bob. That didn't work at all. What happened there? See, look at that. See, it says, wow, that's my name too, but that's not correct though, because string compare, I wonder. Ah, intriguing. So it looks like string compare. You can't just do it this way. We actually have to do equals 0 maybe. Oops, keep that there. There, it works now. Yeah, to do equals 0, because 1, I guess, is true and 0 is false according to C. Yep. So there we go. And now I'll quickly show you the memory of this and show you how it all connects together. So we're going to go to the memory here. I also have to update my tool too, because if I right click and go to heap, it still goes to the data segment. So I actually have to I have to update my code. So we're going to first go to the code segment, so you can see the code here. So that's the header. The code starts usually at A9, because A9 is part of the startup code that actually runs it. And you can see here that we have, yeah, see, that's all the data. That's all the library code basically to do all of that. The CMP function, etc. It's all in there. C program is quite big. And then here is our here's our data down here. I do believe that's our data, right? And this is the kernel. No. This is actually the this is the heap. So here's the heap here. So here's our kernel. This is from the ls function, so don't mind any of this stuff down here. But this is our heap right here. Our variables that we declared. And then if I go to here, this is our data segment where we have pointers. So here there should be a pointer to the heap, I believe, that would point to what I just specified there. So if we look carefully, let's just go back to the code segment for 1 second, and we just determine where this is. So it's right here. So we have 0, 1, 2, 3, 4. So it's at 4. So 0F04 I should see in here. So 0F00, 0F. See if you can spot 0F04. Huh. It's probably not stored. Oh, because it's only a local. Because the memory we allocated is actually, it would be in the C stack. And the C stack is, well, way at the end of our heap. So our heap ends right around. No, it doesn't go that far. Shouldn't go this far. No. Our heap. We have a lot of heap space there. Heap should end right around here, I would imagine. Just saw something flash by. Yeah, there it is right here. Here's our variable. There's our pointer to my name. And then these are the rest of the heap here. So these are the other variables that are sent in through the C stack, because these are all local variables. If you created, I believe if you created global variables, then they would be in data. So the stack contains a lot of your stuff. So this is why the data segment can easily be 1 page, 256 bytes, and you shouldn't have to worry about it. So, but yeah, so that is, I guess, as much as I want to go through today, because I don't want to make this video too long, but I would have loved to go through some of these, like the get param, for example, which is super easy to use, and then the load file, etc. Well, I guess I could quickly show get param. Get param is pretty easy. So if I do this, if I do char star p, I just got to go p equals get param. That's all I have to do. I have the parameter. So then you include heos.h, and we have get param, and then we can just do puts. Your parameter was. Then we'll do this down here if we don't have to worry about doing c put c, and then do puts p. Save it. So this example, you use parameters in your C code to grab stuff. So we're going to do it again, make hello, copy it over, very quick, and then run hello 1, 2, 3. Look at that. Your parameter was 1, 2, 3. Blah. Ta-da. And you also clear screen a bunch of other things too, like clear screen works, and you can put characters at certain locations. There's a lot of the C functions that you normally would use in C. A lot of them are working in the C for Hacker's Edge here. So, and then at one point you will be able to literally run CC65 in game as well as CA65 in game. CC65 will generate an assembly file, then finally you go CA65. Oh, actually there's one more thing I do. I'm pretty bad at. There's one more thing I do want to show is the map file. So what we're going to do here is I'm going to manually run some of these things. We're going to manually run CC65 hello.c. We're going to go CA65-m hello map. Then we're going to go hello s. No, it should be map. It should be called map, or is it -map? Oh, no, it's not this one that does it. It's the linker. It's the linker that does this. So yeah, we do CA65 hello.s. So Then we do L. Actually, I'm going to grab the other one up here. So, okay, and then -m hello.map, and then I don't want to take too much longer, so then do that. Okay, now if I go cat hello map, you can this is what I kind of want to show you. This is all the imports that your code's using. The map file is very, very helpful. I might put that in the make file natively. It is currently available in my other make, in my personal make file, so I might put it through here. But here you can see everything that's being used and called. It's very helpful for debugging purposes, like super helpful. Like as you can see, there's just lots of goodies here that make it. Like you can see std in here, right? You can see a lot of. You can see exactly how everything is put together. You see the heap information. Yeah, there's lots of goodies here. The constructor table, deconstructor table, the heap stuff, and then here is the most useful information up here. Is the exports by name, and of course your segment list, and then you up here you even have all your where all the code is located for every component. So you can see everything that uses data. So you can see what uses data everywhere. So if your data is running out and you're like wondering where's my data going, you can take a look quite easily and determine what's going on with data and things like that. But you should see that hello H uses, the hello program we just created uses no data at all. So player custom code should not use data. It essentially is going to use the code, and it's going to use read-only data, RO data. And that's really it for that. And then here is the header, and then the startup code. The header is 8 bytes. Startup code is 15, that's hex. So, and then you have a bunch of other things. So, yeah. But yeah, the exports by name is super helpful for understanding exact locations in memory where a lot of these things are. You can see that that's located there. You can see where the main function is located. So the main C code starts at 83B. You can see the startup. You can see the startup code is actually you can't see. So we can see ECCS start, data run, the heap size. Everything is listed here. You can see the put statements where it's located. You can see where your standard in's located. You can see where everything is. Yeah, you can see where all the pointers are located. It's quite neat to be able to look at this and go, wow, this is everything that your C program. That is what everything a C program uses. And bear in mind, it's the exact same program we created in assembly 2 days ago, and it's amazing how much larger a C program is. But this is one of the reasons why I'm going to be updating the kernel to Hacker's Edge kernel 2.0, because it is going to make C programs much more smaller, because the kernel itself is going to include a majority of the helper functions. So a majority of these functions are all going to be stored within the Hacker kernel. So the Hacker kernel will essentially have an export for all of these functions here. And then the C library is more or less going to be just a small shim that's going to have lots of address jumps. So when you do a call to puts, we do a call to gets. When you do a call to most of these things, all that's going to happen is your C program is going to do basically a JSR directly to. If you go hello S here, if you cat the assembly version, you see all these JSRs. These JSRs jump to all these locations here. So all of these type of things will be put into the kernel. So these JSRs will jump directly into the kernel to basically do all these things. So it's going to make the C programs very, very compact and small. Assembly programs can also obviously easily use a lot of these functions as well, but it's going to be mostly make it easier for C programs to be smaller. But anyways, this video actually is getting really long right now, a little too long. What video size am I at now? Oh, 44 minutes. Yeah. Okay. I don't want to make the video too much longer. So yeah, so that is the gist on how to get C coding started in Hacker's Edge. Just download the CC65, download the zip file that I just showed you guys, and compile away, and you should be able to import files using the import function if you follow the directions I showed you, or use FTP and upload the bin file directly. Hopefully I'll have the compiler built into the game soon, along with being able to having the FTP server working a lot better soon. So yeah, that's the end of this video. So hopefully it was very informative for everybody.